request Dr. Siddhartha Sarkar to start his lecture.
Yeah, hi. Okay, so before I start, I think there was a question yesterday about this why we take the accumulation point in the definition of limit. So I just realized that this is much easier to realize from the definition. So let me just quickly. I have to. Okay, my screen is visible now. Hello.
Yes.
Okay, so I don't remember who asked this question. So if you, the problem was if you don't take this accumulation point instead of, if you don't take the limit point, the problem would be the definition would be invalid. So if you look at over here, this definition, so you need this value norm of fx minus b to be less than epsilon. So if you take a continuous function and at some point, you just delete the value and put a very high value over there. So this difference at that point would be very high. If you allow your x equal to a at that point. So in that case, you have to take that. Okay, so then in that case, x equal to a, it will contradict the definition. So this won't be less than epsilon anymore. Because f a and b would be very far apart. Okay, so let's start with today's lecture. Okay. Okay, so what you are going to do today is the main aim is discuss some more on derivatives, but because we have seen earlier that the concept of derivative is quite difficult to incorporate in a sense that this is a linear map, and departing from calculus where it was just a real number and you would just try to test whether that limit exists or not, and then confirm whether the derivative exists or not. So checking something like or expect that okay, so there is a linear map and I'm going to check whether this linear map is going to give me the derivative or not. It's a tedious task. So you need some kind of results which would make your life easy. So this is the reason why we are what we are going to discuss today. Essentially, at the end of it, we'll discuss some kind of necessary and sufficient conditions. Okay, the one way would be it's not the same condition. You need little bit stronger when you go to the sufficient condition. Necessary condition would be easier. Okay, so let's start with the definition of directional derivative. So these ideas are going to eventually give me what we are going to discuss. So directional derivative is usually should be thought of as a derivative along certain vector. So what you need again, you start with my function is always from some subset of Rn to Rm. And as we noticed, you need an interior point to basically talk about some derivative or even some kind of partial directional derivative at that point. So what you are going to do is you take any non-zero vector in Rn and you're going to define the directional derivative in the direction of u. So it can be thought of as, so you are approaching A. So in this, remember the definition of derivative says that you have to look at this particular definition over here. So instead of this definition, it was just limit h tends to 0 as vectors, f of a plus h minus fa, and that is going to slowly getting around some linear map. Okay, so you're still approaching A, but something like along this vector. So you can think this T converges to 0 in this definition should be thought of as A plus TU converges to A, but along this vector U. Okay, so the definition says instead of looking at a very complicated derivative, what you do is just take the limit T tends to 0 and then take this particular expression f of a plus tu minus fa and divide by t and then compute its limit. Okay, so you have to be slightly cautious over here because the numerator in this particular case, which is I'm writing as f of a plus tu minus fa, this is a vector in Rn and the denominator is a scalar. So this particular expression within the limit actually means that you are looking at a vector multiplied by a scalar 1 by t and looking at limit as t tends to 0. And because t tends to 0, will again assume that it's an accumulation point. So t equal to 0 is not allowed. And then try to see whether this limit exists. Okay, so this one is called the directional derivative of A in the direction U. But of course, to make it, if it exists, then only you define it to be the derivative. Okay, so we need to kind of try to understand, we'll try to understand that what is its relationship between the original derivative, which is a linear map. Okay, so let's try to figure out some example first. So you think of this function R2 to R defined by x1 square plus x2 square. So there was an exercise earlier in the lecture 1. So from that lecture, you can you actually have computed the derivative of this particular function at any arbitrary point. Okay, so there is a typo over here. There should not be a dot. There are just 2 entries over here. Okay, so in this example, generalized for x1, x2, xn, you have actually computed the derivative of this. And this turns out to be at a1, a2, the derivative is a linear map which sends the vector x1, x2 up to xn mapping to 2a1, x1 plus 2a2, x2 plus up to 2an, xn. So this is already coming from that exercise. And now let's try to check what happens if I try to find out the directional derivative among the along the axis. Okay, so let's try to put these values in the above definition over here. You see it is f of a1 a2 plus t times 1 0. So that is f of a1 plus t comma a2, and you're subtracting f of a1 a2 dividing by t. You just plug in the values of this map over here, subtract all the possible coefficients, and then it turns out it's a clean expression 2a1 t plus t square. If you divide by t, this turns out that this limit is just 2a1. And a similar calculation will tell you that the derivative at directional derivative at the point a1, a2 in the direction of y-axis, it's 2a2. Okay, so over the y-axis, you are getting the coordinate, which is this number 2a2, and along the x-axis, you get the coordinate, which is this 2a1. Remember that this being a linear map, I can always write it down as the pair of vectors 2a1 comma 2a2. This is a matrix representation of that linear map if you take the canonical basis elements. Okay, so what is happening here is that some mysterious way I'm kind of ending up computing the derivative being a matrix representation, which is a vector in our case, and I'm trying to actually compute the dot product of this with the vector along which I'm computing the directional derivative. So this way I'm actually recovering the vectors coordinates of the derivative vectors over here. So the question is it always possible to recover it like this? So the next result says that, well, it is actually the case. This is not a surprise. So if you see over here, so directional derivative of at the point A in the direction U is nothing but the usual derivative as a linear map evaluated at U. So in this particular case, this turns out to be the dot product over here. And remember this, to establish this theorem, you need these directional derivative and your derivative to exist. Of course, you need to know that from the hypothesis that the function is differentiable at that point. Then only you can guarantee that the directional derivative exists and it is as desired how you are computing this. Okay, so the theorem requires the following thing. You need a point in a subset of Rn, and that point should be again interior point, because you need to define the differentiability at A. The property that A is an interior point is already encoded in the definition of differentiability. And then you take any non-zero vector, and the directional derivative is by definition. So for directional derivative, you need to kind of compute some quotient like this. Okay, let's try to come one by one. So my hypothesis says that the function is differentiable at that point. So what does it mean? I'm guaranteed to have a linear map which satisfies this property. Okay, so limit h tends to 0, norm of some complicated expression divided by norm of h, this limit should be 0. Okay, so because this limit is 0, what I can do is, well, my target is to prove that this quantity is less than epsilon. Okay, so to have the directional derivative exist, I need to kind of make sure f of a plus tu minus fa divided by t, that gets close enough to f prime au. Okay, so you start with any positive epsilon, and I'm going to manipulate this a little bit. You divide by norm of u to this epsilon, so that still stays as positive. And now you use the definition of derivative in this particular epsilon, namely epsilon by norm of u. Okay, so the definition says that as long as you are in the deleted neighborhood of 0, which is delta, then this quantity is less than epsilon by norm of u. Okay, so this just follows from the definition of derivative. Okay, so given any epsilon positive, I'm taking the modified epsilon and there exists a delta so that this happens. Now what I'm going to do is that I'm going to use this entire expression to achieve what I want to, what I desire. So you modify the delta, you already got a delta. So you modify the delta being delta by norm of u, which is still positive. And then take any t so that your mod t lying between 0 and delta 1. So if you do this, I'm trying to test it on the vector, the scalar t times the vector u, okay, which is h. So you plug in the entire thing. Over here, you end up seeing that mod of t, norm of u, that is less than delta 1. And that means your norm of h from the property of the norm of a vector, norm of h would satisfy this inequality now, right, because of the scaling. Now if you do this, now this line has to be true. So instead of h, you replace everywhere t times the vector u. So what you get is this is less than epsilon times norm of u. Now from the denominator of the left hand side of the inequality, you just adjust your t, put it inside, and watch out that this f prime a is a linear map, so you can take t outside this. If you bring t inside, this turns out to be something like this expression. Okay, in that case, you are also cancelling norm of u from both sides of the inequality because that's a positive real number. So you end up getting something like this. And actually, this is what you wanted. You wanted the directional derivative at A in the direction u should be equal to f prime A evaluated at u. This is what you ended up doing. Okay, so question is, what is the use of a priori use of, okay, forget about what we are going to do about derivatives and so on, but a priori there are, what are the applications of this? So first of all, this is a this to guarantee that derivative. So this basically says that this existence of directional derivative, if they exist from all directions, whether function would be differentiable or not. The theorem is actually doesn't say anything. It actually says something about the converse of this. Okay, so you need the differentiability to happen, then only you can guarantee the directional derivatives exist. But however, if I want to test something like that, the function is differentiable or not, how am I going to use this? So of course, this theorem, the statement of this theorem, I can just make it a contrapositive statement saying that if I can make sure that one of the directional derivatives does not exist, then that would guarantee that derivative does not exist. Okay, so this is, you can see in the following example. So you take R2 to R, the function which is defined by xy by x square plus y square when my point is away from the origin, and the value of the function is 0 around that point, at the point origin, and we are trying to compute the directional derivative for any arbitrary vector. So at the point origin, of course. So let's try to do this by our usual formula. It is by definition limit t tends to 0, f of the origin plus t times the vector u, which turns out to be something like this, f of tu1 tu2, and minus f of origin, which already vanished because of the definition. And then you plug in these values in the definition, and what you get is, instead of the value you get at the point xy, you get tu1 tu2 divided by t square u1 square plus t square u2 square. So from denominator and numerator, you just cancel the t squares, but still there is a t in the denominator which stays as it is. So you get this limit. So limit of 1 by t with some constant. Okay. However, let's look at this constant first. So let's say I have a point which is other than this two, 1, 0 or 0, 1. But then this constant actually is some fixed constant u1 u2 by u1 square plus u2 square, which is not a 0. The moment that happens, that this limit actually blows up. Therefore, it doesn't exist. Well, but however, the directional derivative actually exists at the point 1, 0, because if my u1 is 1, u2 is 0, this particular constant is 0. So you are evaluating limit t tends to 0, only the coefficient 0. So that would exist. So the directional derivative of at origin along the direction of the x-axis or y-axis, they exist. Both of them are 0. However, if we take any other direction, arbitrary direction, that turns out that this directional derivative does not exist. Well, so from this I can immediately conclude that the function is not differentiable at the origin. Okay, actually there are some other ways to prove that this function is not differentiable. For example, you can try to prove that this function is not continuous at the origin. If you try to, this is more or less something like very similar idea. If you try to approach from through a vector u, which is u1, u2, about the origin, then this quotient xy by x square plus y square turns out to be some constant, which differs if you take a different constant, different direction. So for instance, if my slope of a line around the origin is lambda, you end up getting some constant which is lambda by 1 plus lambda square. And that differs if you change lambda. So therefore, this analysis would say immediately that the function is not at all continuous. If it has to be differentiable at the origin, it has to be continuous at the origin. So it's one of the results we have seen in the last lecture. Okay, so that way also you can prove, but this is a much easier check. One line check, immediately you can conclude that the function is not differentiable at the origin. Okay, so let's try to think of a converse of this. As I was saying that, okay, so if I assume in this theorem that the directional derivative exists, let's say, from all directions, does it guarantee that the function is differentiable? Unfortunately, the answer is no. And you can again see an example. You again take this a function from R2 to R, just define it by x square y by x power 4 plus y square. Okay, in case it is not at origin and 0 at the origin. And then again you compute the directional derivative along any arbitrary direction u1, u2 at the point 0. What you end up getting is some expression like this. If you try to clean up that, you get some expression like this: e1 square u2 divided by t square e1 power 4 u2 square. So in this case, there is no t on the numerator and there is only one t square in the denominator. This limit actually would exist. If I guarantee my u2 is non-zero, what would happen is even if u1 is 0. If u1 is 0, then the entire thing is 0. If u2 is 0, the entire thing is 0. So therefore, the limit would exist. So if u2 is non-zero, irrespective of what u1 is, you get e1 square by u2. But if u2 is 0, luckily, the way we have chosen the example so that the entire thing becomes 0. So you are again computing limit t tends to 0 of the constant 0. So the limit still exists. So in this case, the directional derivative exists from all directions. Now, how do I see that the function is not differentiable? So as I said that this is a kind of a tedious task. But let's recall something. What we proved actually is if f prime 0 exists, suppose it exists, then that has to be a linear map from R2 to R. And from the previous theorem actually tells you this should be this map. U maps to the derivative at 0, and this linear map you compute at the point u. And that turns out to be your directional derivative at u. So if it exists, then this particular map, u mapping to f prime 0 colon u, this should be a linear map, assuming the derivative exists at the origin. But you already seen how the function look like. It is just a function which at u2 non-zero you get e1 square by u2, and if u2 is 0 you get 0. This cannot be a linear map. So this one again, just a clever use of the theorem, immediately guarantees that the function is non-differentiable. This is also sometimes useful. Okay, so one of the most interesting application, okay, so we are slowly coming towards the necessary and sufficient condition to achieve that. And then we need to define something called the partial derivative. So I'm just writing it as DIFA. Sometimes people use a notation del xi of f computed at a. This is exactly the same thing. So how do I see this? What is DIFA? DIFA is nothing but the directional derivative along the ith axis to the direction to the point A. Okay, so by definition, this is just f of a plus t times ei minus fa by t, where ei's are the canonical basis vectors of Rn. Okay, let's try to analyze this a little bit. How do I see whether this is a partial derivative or not? If you try to cleanly write this expression a plus TEI, you will see that this looks like this. So except for the ith coordinate, everything else is that coming from that constant point A, and the ith coordinate become AI plus T. So if you try to compute a limit of this, this is nothing but your partial derivative with respect to the ith variable at the point a1, a2, an. So this is what it is. The directional derivative along the axis ei is nothing but the partial derivative of f at the point A. Okay, so now if I assume, let's say, that if my derivative exists at A, okay, so then earlier what you have seen is that if the derivative exists, then the directional derivative in the direction ei should be this quantity f prime ai, which is nothing but d1 fa over here. Okay, so now you remember that f prime a, if I try to write down in terms of coordinate axis, okay, in the linear map, you take it to the matrix with respect to the canonical basis elements. What you end up getting is this real numbers over here. Okay, in this particular case, I'm actually looking at the derivative, okay, not the global derivative or the general case of the derivative. You're actually looking at the derivative of a function which look like a to r, not a to rm, by the way. So we actually define the partial derivative of a function from some open set in open, not necessarily open set, some set in Rn to R. So then in that case, this turns out to be a real number. So this plug in these real numbers and you end up getting the derivative of this function. This is something very important and crucial because when we are going to talk about the proofs of those last few results, sufficient and necessary conditions, we are going to use this. Okay, I'll just pause here. If there is any confusion or question, I can explain. Any question, anyone? Okay, if there is no question, I should go ahead. So I should want to mention one of the immediate application of these partial derivative. Remember, the definition is I have a real valued function. Ith partial derivative is the directional derivative of this function in the direction of the axis ei. Okay, so this theorem says if you take a subset in Rn and pick a particular point A, which is an interior point. Let's say I have the assumption that f has either a maxima or a minima at that particular point A. Okay, and assume that the directional derivatives at A from the directions, the canonical axis, they exist. So then immediately it says that this DIFA vanishes. Okay, so that is kind of almost clear from what we just discussed. So if I try to prove this vanishes, you basically try to prove that this limit vanishes, but this limit is actually a limit of one variable function phi ix. You are computing at keeping this ith coordinate apart from the ith coordinate, all the coordinates fixed, and only the ith coordinate varies. Now, the assumption says if has a extremum at A, this basically tells you that the one variable function has an extremum at A. And there is a extremum value theorem for calculus, which immediately tells you that the derivative of the one variable function should vanish at that point. But the derivative of this one variable function is nothing but this particular value, which is your DIFA. So that should vanish. Okay, so again, I should ask a question that can I get some kind of converse of this? So unfortunately, again, the answer is no. Even if you guarantee that DIFA vanishes, that and let's say DIFA exists and vanishes, that doesn't guarantee that if has an extremum at this particular point. Okay, so this can be seen as some kind of function over here. Fxy is kind of tube like okay, so it's not a tube. So let's see the picture how it looks like. It's I think it's called some kind of hyperboloid of one sheet or something. So if you try to draw it in 3 dimension with the values go in the z-axis, the function fxy is x square minus y square actually look like this. So what happens if I try to examine, let's say what happens around the point 0, whether it has an extremum or not. Okay, so around this point, if I just examine, then for example, if I take the cross section around the through the x-plane, you basically end up getting y equal to 0, and then you are examining the parabola which is given by x square. So this is the red curve over here, and if we just try to look at through xz axis, this function has a minima at this point. Okay, and now if you try to do the same, keeping y equal to 0, sorry, x equal to 0, so the function takes a form minus y square. So the minus y square graph actually looks like this in the green dot, in the green color over here in the graph, and that has a maxima at this point. So both the extrema and actually exist at that particular point origin. So D1FA and D2FA, this particular case, both exists and would be 0 because in one case it is a maxima, in another case it's a minimum. However, if you look at the graph in a global way, you see that you can immediately find out the values are going up through the z-axis. Around the z-axis, there are this is look like a point of inflection. So there are lots of points going down over here along the green curve, and points which are going up through the red curve. So that shows that the function neither has a maximum nor has a minimum. So it's not an extremum. Okay, so that immediately tells you that DIFA guaranteed to be 0, they exist. That doesn't guarantee if has an extremum at that point. Okay, so now we are going to turn to how do we prove that something like the existence of derivative out of some condition or some kind of converse to this. So first thing what we are going to do is that we are going to prove the following result. Let's go to the result first. So we are going to prove if your derivative exists, then all the partial derivatives along with some kind of canonical functions which I am going to describe, they would exist, and there is a nice form of the derivative which can be easily written down in a neat way. So that tells you that, okay, if I want to compute the derivative, what you need to do is that I look forward to some kind of coordinate functions look at their partial derivatives, whatever the scalars I obtain, I just throw it in some matrix form, and this matrix is going to give me the representation of the derivative, which is a linear map from Rn to Rn. Okay, so what are those maps Fi? Let's try to go through it. So you take any subset of Rn and a function from A to Rm. So the coordinate functions are basically the following. So if you see the value of f at any vector, that's actually the column vector of length m. So this can be written as a column vector with m entries. So I'll define the ith entry of this function fi, and I'm going to call these as the component functions of my original function f. So in particular, this function fi is nothing but you take the function f and compose it with the projection at the ith coordinate. Okay, so that's what gives you the ith coordinate of this function. Okay, so here again there is a particular result from linear algebra which you can easily prove. Let's say you take a linear map from Rn to Rm, of course, with respect to canonical basis of Rn and Rm, you should be able to write in a matrix form, which I am denoting for time being as a curly bracket T. So curly bracket T means a matrix representation for T as a matrix with respect to the canonical basis elements from both sides. Okay, so the question is, how do I recover the ith row vector for this? So the statement says the ith row vector of this is nothing but if you just compose this linear function, post compose it with the ith projection, what you end up getting is some linear map from Rn to R. It has a matrix form which is a vector of length n. Okay, so this is going to be the matrix form of the linear map pi I compose T. So the rows of a linear map represented in a matrix form is nothing but the matrix representation of that linear map post composed with the corresponding projection maps. Okay, so this is going to be very useful for us. So this theorem says if you start with a subset of Rn, and again you have to take an interior point because you want to guarantee the differentiability. Let's say your function is differentiable at A, then it guarantees all the partial derivatives of these this component functions if A should exist at that point. And if I plan to write the derivative in a neater way, so remember this dj if IA is essentially some real number, because if IA is a real number, if IA is a real valued function, if I is a real valued function, if you can see over here, this f1, f2, if m are the real valued function. If I look at the directional derivative along the canonical axis, this turns out to be a real number. So all these dj FIA, they're actually real numbers. Now describe your dj FIA as the ijth entry of the matrix, and the theorem says this is it. This is how we are going to obtain the derivative in the matrix form with respect to the canonical basis. So this theorem is kind of very useful. Of course, this talks about a converse direction. It doesn't guarantee you that the differentiability of this function, but what it says is that if you know somehow that the function is differentiable, it tells you that how to compute that derivative at that particular point. Okay, let's try to go through how to prove this, which is not so difficult. So first of all, what I'm going to do is, remember my fi is nothing but pi I composed with f. So let's try to apply the derivative of pi I composed f at that particular point A. So you have seen the chain rule in the last lecture. The chain rule says this is nothing but pi I prime computed at fa and compose it with the linear map f prime A. Well, now recall that if we pick any linear map, the derivative of the linear map for whatsoever point you choose, that turns out to be the same linear map again. So this pi by prime fa should turn out to be pi I itself as a linear map. And so this means that if I prime A is nothing but pi I composed with f prime A. What you have to do is just now use this particular lemma over here. So if I compose with pi I to a linear map, what you are going to recover is the row vectors of this matrix form of f prime A. So this is what this theorem actually tells. So f prime A, if I write it in the matrix form, look at its ith row, what I am going to get is the derivative of fi at the point A, right? So it's kind of enough then to prove that this one or otherwise this one, fi prime A, is nothing but this row vector. Yeah, anything, any question? Sorry. Okay. So this is what I'm going to prove. But somehow this tells me that the function, this reduces the entire thing into m equal to 1. So how do I see this? So remember now what you ended up proving is that if I prime A, let's say I assume that I have achieved this proof for m equal to 1. So in that case, my just concentrate to that particular function fi, and then you end up getting this particular row vector, and then go to this line, and then this says that the row vector of the arbitrary function f prime A turn out to be the row vector this. So what I need to prove is that this theorem, if I can manage to prove assuming my f is mapping A to R, then I'm kind of done. And this is already noted down at the point when you are defining the directional derivatives. Let's go back over here. Yeah, so you remember we spoke of if my f prime A exists for some function which is from Rn to R, then difa exists and the derivative of that function from Rn to R turn out to be this particular row vector. So this is what I wanted over here. Okay, so this theorem is now proved. It says that, okay, if you want to compute the derivative, what you need to do is that you look at the component functions and you look at their partial derivatives for each variable, and then you align it this way. The jth partial derivative of the ith component function, that turns out to be a real number, and which gives you the ijth entry of this derivative. Now the question is, well, this doesn't guarantee the differentiability. This just says that if the derivative exists, then we should be able to realize a derivative this way. Okay, so we are going to need some kind of converse of this. So what should be the converse? It says that can there be some conditions on these partial derivatives so that this guarantees that the function is differentiable at the point A. So I actually don't need to write down, please keep in mind over here, I don't need to write down what the derivative would be taking a shape, because that is already guaranteed by the previous theorem. So if the derivative exists, then this should be expressed in the following way. Now this one just says that some condition I require to ensure or guarantee that differentiability at that particular point A. So the condition says again as follows. What you need is, again, you start with some subset of Rn, you take an interior point, you take a function from A to Rm. What you need to do is that, suppose you assume that dj fi x being a function of x, they exist and continuous in a neighborhood of A. So this somehow guarantees that I would be able to make sense of dj fi in some small enough open ball around A, whatever small it could be. So therefore, I should be able to make sense of this dj fi x in some kind of open box around A. Instead of ball, I mean, I can always inscribe a box inside a ball. And that way, some kind of suitable neighborhood I can talk of, and where the function is as a partial derivative function, it exists and continues. Okay, but before I do this, again, this is some kind of analysis of this difference. So before I do this, let's recall some standard theorem of calculus, which I'm going to record. So you take two pair of real numbers a less than b and consider a function f from the closed interval ab to r. You assume that the function is continuous on that entire closed interval and is differentiable on the corresponding open interval. Then it says that there should be a point where the function has the following property. Its derivative should be expressed as fb minus fa divided by b minus a. Okay, so this comes from, usually, as far as I recall, this comes from the Rolle's theorem, which you can easily prove. And we are going to use this over here. So we are going to kind of boil down everything to one dimension and achieve this particular thing over here. Okay, so let's try to examine the difference f of a plus h minus fa. Okay, so first of all, this is written as f of a1 plus h1 up to an plus hn minus f of a1 up to an. So what I'm going to do is that I'm going to manipulate it to express. So first, the rate expressions are the old ones. F of a1 into an with a negative sign is this particular thing over here. The rate expression in the last line is also over here. Everything else what I'm going to just write down is just kind of some adjustment. Okay, so the blue ones is going to the cancel with blue one. This pink one is going to cancel with this pink one. So what are these terms? So the blue one is basically, first you try to increase the first coordinate a little bit and keep everything constant. So this is what it is. A1 plus little bit of H1 and keep everything constant. And what I'm going to do is that apply mean value theorem on this, just keeping in mind that this is realizable as a real function, as a function with one variable function. Okay, so there is still a catch over here. These values could be vectors. So there is a little bit of argument required over here, which we kind of more or less have seen in the previous theorem, that this is enough to prove this particular theorem in the case when m equal to 1. So this is what I'm going to do. If I assume m equal to 1, these are all basically some real numbers and we are making some adjustments. So I have no problem applying the usual mean value theorem of calculus. So now again, if I have increased the first coordinate a little bit, keeping everything constant, the second in the pink, I'm going to keep the first coordinate constant, which is the increased form, a1 plus h1. And then the second coordinate is increased by h2 and everything else is fixed. So keep on doing this way, you end up getting something like expression where everything varies and the last coordinate is constant, and you just adjust it with this first term over here. Okay, so now layer by layer I'm going to apply the mean value theorem. So first you examine this first line. Okay, the first line is if with the first coordinate increased and everything else is constant. So the mean value theorem says that if I kind of realize it as a function which is written down over here, x mapping to f of x and remainings are constants. So then this being a function difference of phi of a1 plus h1 and phi of a1. Now what can I assume about this particular function phi 1? Well, this is nothing but, so if you see that, recall the definition of the partial derivative, it just says that d1f is nothing but the derivative of f1 at the point a1. Okay, so there also we kept this the second up to nth coordinate constant and only varied the first term. So d1f, if I guarantee that d1f exists, then I should be able to write this, but wait, you need a little bit more. d1f exists, and how do I achieve, where am I using this continuity of this? So you are basically assuming that d1fx exists and continuous in some neighborhood. So look at this theorem again. So this says that I need the differentiability of this, that is guaranteed by that one, and I need the continuity. The continuity is seen as between the interval over there was AB. Let's talk about the interval A1 and A1 plus H1. Well, you have to be careful over here because I don't know what H1 is. It could be either positive or negative. So if it's H1 is positive, you are peeping into the interval A1 and A1 plus H1, A1 comma A1 plus H1. And within this, the function is continuous and differentiable. So I can immediately apply mean value theorem saying that the difference should be, this is phi a1 plus h1 minus phi a1. This should be written as the difference of the interval, which is now h1, times the derivative at some point in between, strictly in between these two numbers. So which I am just taking it to be some xi1. Okay, so if I have this particular equation, I'll keep it this way, and for sake of my convenience, I'll name it in a way. So I'll call these particular vectors I1, A2 up to AN, being this vector C1. So this says that the first line of this particular expression should be written as H1 times some d1f computed at this particular vector C1. Similarly, I can continue doing this. The second line is this. By mean value theorem, that should be equal to h2 times. Now this is the second partial derivative. Here you are keeping your a1 plus h1 constant and a3 up to n constant. So there should be some xi2 in between a2 and a2 plus h2, so that the derivative of that particular one variable function times h2 is the second line. And you keep on doing like this. So let's try to write it in a more general pattern. So the ith line, I should be able to write it as hi times the partial derivative of f at ci. Okay, so now we are going to write the final expression. So remember, if I want to guarantee the derivative exists, then what I need is some kind of linear map over here. So f of a plus h minus fa, and then you subtract by some linear map computed at that particular point h. Okay, so what is the linear map over here? So you take this linear map, the n coordinates actually going to this scalar d1fa times w1, d2fa, that's a scalar again times w2, and dnfa, that scalar times wn. So keeping these partial derivatives as some kind of fixed constants, you get a linear map over here. So this is the linear map I'm going to test it on, whether this turns out to be the derivative or not. If you carefully look at the statement of this theorem, this is nothing but what you are expecting. Okay, so let's try to do this. So in this case, this is the function is one variable. I put just a mod on the numerator. Denominator is still norm of h. I'm going to write down everything what we have got from these lines. So each of these lines are of this form, hi dot difci, and then this then takes this sum form, summation I1 to n hi times this difci, and I'm subtracting it from this linear map evaluated at the point h. Okay, so now let's try to carefully analyze our numerator. So there is a hi common over here, so I'm going to take it out with a modular sign. Then it turns out that this is the difference. And mod of hi, remember that this is always smaller than or equal to norm of h. Because what is norm of h? That square root of h1 square plus up to hn square. So this is nothing but telling that hi square is less than sum of h1 square up to hn square. Okay, that's anyway true. So this particular first term, mod hi by norm f, h, this is smaller than equal to 1. So I make it little larger like this. So I still keep this limit in front. And then I observe that if my h is slowly converges to 0, what is going to happen is each of these hi are getting squeezed around 0. If that happens, my xi i's are going to be squeezed around 0. Okay, in a sense, my ci's are actually squeezing around a. So as h tends to 0, for every I am going to get ci tends to a. And then I am also assuming the continuity of DIF. So this means that this sum is converging to 0. So that means the right hand sum is going to be 0 with the limit h tends to 0. So therefore this limit exists, and hence the function is differentiable. Yeah, so far what you have got is, this is what one of the important conclusion. It says that as a necessary condition of existence of derivative, what you get is all the partial derivatives of all the component functions should exist at that particular point. And if you want some kind of converse to this, the existence of those partial derivatives is not going to be enough. What you need is the existence of partial derivatives not only just at this point, but at a neighborhood of this point, and they should be continuous. So it doesn't exist at just around the neighborhood, but in some neighborhood, that being a function of x being continuous also. So djfix as a continuous function, they should be, you need that. So assuming both of this gives you a converse of that. Okay, so I'm done, and I'll open up for any question. Yeah, questions, anyone? Hello.
Yes, sir.
Yeah.
Yeah. Any question? If no question, then let us say thanks to Dr. Sarkar for a nice lecture, a nice material. Uh, let us clap for it.
Thank you. Thank you very much.
Thank you, sir.
Yeah, you're welcome.